Let's take a look at Chapter 8, Equilibrium and Elasticity. We're going to be working on problems like this of how things can remain in static equilibrium. Section 8.1 is on torque and static equilibrium. Two conditions for static equilibrium on an extended object, such as these rocks and boards, is 1, the net force on an object must be equal to 0. You will use Newton's second law, sum of the forces, and set them equal to 0. The second condition is that the net torque on an object must be equal to 0. You will use this criteria, number 2, sum of the torques must be set equal to 0. For an object in static equilibrium, the net torque about every point must be 0. The object must not move. You can choose any point you wish as a pivot point for calculating torque. However, there is one point that is better than another point, and we'll take a look at these examples. Quick check 8.1. Which object is in static equilibrium? How do you handle this problem? Well, you want to know the sum of the forces is equal to 0. Therefore, look at the vectors. You want to make sure the size of the vector is equal to the ones on the other side. In the case of A, we have a same size vector. Let's just call it 1. Give it a magnitude of 1. So we've got 2 of them going to the right, so that would be a 2. And we have 1 of the same size going to the left, that would be 1. That is not in equilibrium. Let's try B. You got 2 to the right, 1 to the left. Once again, not in equilibrium. Let's take a look at C. You got 2 to the right, and you have 1 big one to the left, but it's the equivalent of 2 small ones. So we got 2 on the left. So this one works. Now we look at the same side, the D. You've got 2 on the right, and the same thing, 2 big ones on the left. So now we have to decide between C and D. We have to enact the second condition, which is the sum of the torques must be equal to 0. We need to choose a pivot point. We're going to choose the center of the block as our pivot point. So you want to find the net torque. What will cause the twist? Well, you want to find R and F perpendicular. So you've got an R coming up this way, and then you've got a big F going to the left. So this R and that F makes a 90 degree, and it's going to cause this block to tumble largely to our left because of the big force F. So we've got a half an R and 2 of the equivalent going to the left. So let's go this way. You've got 1 going up, and on the right, you've got 1 to the right. So it's going to cause a small turn to the right. Now you look at this one. The R in this case is going down because you want the force to be perpendicular to the R. This one is going to cause a small rotation upwards. You're going down and around. So these two are going to cancel each other out. And you're left with a net torque that's going to cause the block to tumble to the left. Well, that's not in equilibrium. So this has got to be entirely out. Therefore, D must be the correct answer. Let's take a look. Let's start with R. We have R perpendicular to F, and that's going to cause a small turn to the right. Here, notice this R is in line with this force. There is no R and F perpendicular, so we don't have to worry about it. Let's look at this one down here. You've got R and you've got F. You got a small r down and your F to the right that's going to cause a small torque to the left. These two balance each other out so that there's no net torque. Therefore, D is our correct answer. Let's look at another example. A 1 ton, which is 910 kilogram bucket of rocks, is suspended from a beam 0.85 meters from a pivot point. A man lifts the beam at the end 3.6 meters from the pivot and holds it steady. How much force must the man apply? What is the force on the beam from the pivot? We're going to neglect the weight of the beam. Well, let's take a look at what we're given. We're given the mass of this rocks is 910 kilograms at 0.85 meters from the pivot point. Now the weight is pulling down. Luckily for us, the weight and the radius are 90 degrees to each other. We calculated the weight here. The weight is the mass times gravity, which is 910 kilograms times 9.8 meters per second squared, which is 8,900 newtons pushing down. So there's our weight. The other thing we're given is that the man is at a distance of 3.6 meters from the pivot point. And the man is lifting everything up. So he's applying a force in the upward direction. We'll call that F man. Now there's also another force, and that force is here at our stand. So our stand must be applying a force as well. We'll call it force at the pivot. So let's put a big symbol here of a circle at our hinge point to remind ourselves where this thing's going to rotate, which is that green circle there. Now that we've drawn our picture and our free body diagram, we know we want to find this force of the man. This is our goal. We're looking for that one. We want to use our equations. Well, the only equations we're given are Newton's second law, some of the forces in x equal to 0, some of the forces in y equal to 0, and our torque equation. Then sum of the torques must equal 0. We have nothing going in the x direction, so we can eliminate that part of Newton's second law. We only need to work at some of the forces in the y direction from Newton's second law and some of the torques. The first criterion for equilibrium is no net force, and we're going to look at some of the forces in the y direction and set it equal to 0 because nothing's moving. What we have going up is the force of the man and the force of the pivot. So we got the force of the man and the force of the pivot, and they're both positive. And what's subtracting down is that force of the beam and the bucket. And we set that equal to 0. The second criterion, we're going to call that equation 1. The second criterion is sum of the torques must equal 0. We'll call that equation 2. you need to choose a hinge point. We could choose the man, but that wouldn't make any sense because we want to solve for the force of the man. So we want to choose the opposite side. You want to choose the point that is not what you're looking for and a point that eliminates as many forces as you can. So we have the one at the corner where the hinge is where we're going to use. So with the sum of the torques equal to 0, you have to look at the perpendiculars of the forces and the distance. We have the entire distance d and the force of the man, and that is going to be distance times the force of the man, and it's at 90 degrees. This force is going to push this thing up and rotate it in the counterclockwise direction, which is positive. Oops, sorry, that's clockwise. Clockwise direction. Clockwise is negative. So we have the force of the man at the distance of the man with the negative sign in it right there. The second criterion, the second force, is the weight. We have this distance here, which is 0.85, multiplied by the weight. They're 90 degrees to one another, so we can just multiply them. And this is going to cause the rotation to go in this direction from R to F, which is in the positive direction. So we add on the force of the bucket times the distance of the bucket, which is at 0.85 meters. Or, 0.85 meters. So we're going to solve equation 2 for the force of the man, and we do that down here. So here's that equation 2. Just doing some basic algebra, solve for the force of the man, which is equal to the force of the bucket times the distance that the bucket's located divided by the distance of the man. We have 8,000 newtons for the force of the bucket. Oh, it says 8,900 newtons. That's 8,900 newtons. And this should be 0.85 meters for the distance where the bucket is compared to the full distance of the beam, which is 3.6 meters. We multiply this all out and we get 2,100 newtons. So now we've solved for the force of the man. The force of the man is 2,100 newtons in the upward direction. So that is part A. Part B is what is the force of the beam? So this was part A. And now we're looking at part B. Well, we just need to substitute everything back into equation 2. Into equation 1. Now that we know the force of the man, we substitute it into the equation 1, solve for the force of the pivot, and we already know the force due to the bucket. We get 6,800 newtons is the force of the pivot, and it's also in the upward direction. Let's look at another example. What does the scale read? Let's analyze the situation here. We have a scale that is pushing upwards, holding up our rod. We also have a 1,000 Newton weight that's pulling down on our rod. We have 2 criteria that we need to solve for. Oh, one more thing, we forgot about the force at our hinge point, the force of the pivot. We have 2 criteria. We have sum of the forces must be equal to 0, and sum of the torques must be equal to 0. Let's look at our sum of the torques is equal to 0. Let's look at why. If we look at sum of the forces is equal to 0, we've got the force of the pivot going up, force of the scale going up, and weight going down. We don't know the scale and we don't know the pivot. All we know is the weight. So we don't really know a whole lot. So let's look at sum of the torques and let's choose an ideal position. Since we know the weight, we do not want to put our sum of the torques around the weight point. We want to put it around a point we don't know and we don't care about. And that's going to be the hinge point here. So let's look at sum of the torques equal to 0 around the hinge point. Well, we need to know our distance. Let's call that L over 2, half the distance of the rod. And we have our force pushing up, and that makes 90 degrees. So we just need to multiply them. So sum of the torques is the distance, L over 2, multiplied by the force of the scale pushing upwards. Now let's look at the rotation. It's going over to the right and up. It's going to twist it in this direction, which is in our counterclockwise direction, which is positive. So we can leave this one as positive. Now let's look at the next one. The next one is the full length of the rod, and it is L. And the weight is W. So we're going to put an L here and multiply that by a W. Since we're going to the right and down, we're twisting in the clockwise direction, which is negative, so we have to put our negative symbol in front of it. And then we set the whole thing equal to 0. There's that 0 that we carried over. Now let's eliminate. We don't care what the length of the rod is, it just drops out. So let's solve for the force at the scale. The force at the scale is equal to twice the weight. Since the weight is 1,000 newtons, the force of the scale should read is 2,000 newtons. Now let's look at a classic ladder problem. You should know how to do ladder problems. A 3-meter long ladder leans against a wall at an angle of 60 degrees with respect to the floor. What is the minimum coefficient of static friction with the ground that will prevent the ladder from slipping? Assume friction between the ladder and the wall is negligible. So let's take a look and draw our problem and draw in our free body diagram. We have a ladder that is 3 meters long leaning against a wall. It makes an angle of 60 degrees with the floor. We know we have weight acting at the center of mass, or the center of gravity. We also have a normal force pushing out from the wall onto the ladder, which we'll call normal force 2. We're neglecting friction here. The only friction we have is in the x direction, which is 60 degrees to the ladder. This is our friction force. In addition, we also have a normal force pushing up from the floor onto the ladder, which we'll call normal force 1. There are 3 equations that we have. Sum of the forces in the x equal to 0, sum of the forces equal to y equals 0, and sum of the torques equal to 0. Let's look at sum of the forces in the x direction first. Sum of the forces in the x direction is equal to 0. We're going to work on the left-hand side. we've got normal 2 pushing to the right, and we got friction pushing to the left. So you got normal 2 minus friction is equal to 0. So we can solve for friction. Our friction force is equal to the normal force of 2. Now let's look at some of the forces in the y direction. Some of the forces in the y direction is also equal to 0. We work on the left-hand side. We have normal force of 1 going up and weight going down. So you got the normal force of 1 pushing up minus the weight going down. And we set that equal to 0. And now we can solve for the normal force of 1, which is equal to the weight. Now the third equation that we need to look at is the sum of the torques. But you need to find an ideal position to take it from. There are 2 conditions you always want to look at. You try not to eliminate the one that you want to use to solve for. We want to solve for friction. So you might think that we don't want to choose this point. The second thing you want to try and keep in mind is that you always want to try and choose the pivot point that has the most forces running through it, which in this case is our corner point. That, taking the torques around that point, eliminates these 2 that are passing through it because we have no R vectors associated with these. Now, although we're trying to solve for friction, we've already resolved that friction is equal to the normal force in 2. And so we did not get rid of this point up here. So we'll come back to this equation 0. We'll call that equation 0 later. So let's look at some of the torques that are going around this pivot point. Some of the torques must be equal to 0. Torque is given the tau symbol, and torque is a vector. And we're going to choose the point that's the hinge point at the bottom, the ladder and the floor. The first force we have is this weight force. We want weight, the force and radius to be 90 degrees to one another. So we already have weight, so we would like to find this distance 1. Well, distance 1 is just related to this cosine angle here. The cosine of this angle is distance 1 divided by the hypotenuse, which is half the ladder. Therefore, solving for distance 1, we get 1/2 L cosine theta. If you have trouble seeing that, draw in a right triangle. Here's your angle of 60 degrees. Cosine of 60 is equal to the adjacent side, which we call D1, divided by the hypotenuse, which is half the ladder. We multiply both sides of the equation by L over 2, and you're going to get D1 is equal to L over 2 cosine theta. Which is 60 degrees. And that's how we get that. Similarly, we can find D2 by using a different right triangle, the orange triangle. To find D2, we use the sine of 60 degrees, and we get D2 is equal to L sine 60. Now we're ready to look at our torques. The sum of the torques must be equal to 0. So let's look at our first torque. Our first torque is this weight. So we know that we have to multiply the weight by the radius, and we want them to be 90 degrees to one another. So that would be this D1, which is L over 2 cosine of theta. Now we have to decide, is it positive or negative? Since the R is to the right and the force is down, it would cause a counterclockwise rotation, which would be positive. So we leave this one as positive. Now we go to the next one. The next one is this normal force. We know we want to put the normal force of 2 in there. Now we need to find the perpendicular radius. The normal force is going this way, and we want to find the perpendicular radius. Well, the perpendicular radius from this point is this distance. So your R is going up and your N2 is going to the right. It would cause this rotation, which is clockwise. Remember, N is going to the right, R is going up. This distance R going up is D2. So we want to multiply by D2, which is L sine of 60. And we've already decided that it was going to go clockwise, which is a negative symbol. So we put the minus sign there and we set it equal to 0. Now let's eliminate variables. L appears in both equations, so we can divide it out. And that's about the only thing we can get rid of. Let's solve for N2. You bring N2 sine 60 over to the right-hand side of the equation and solve for N2. N2 is equal to W, the weight, divided by 2 tan theta. So let's review. We have equation 0, which is our friction force is equal to our normal 2. We're going to call this one equation 1, where our normal 1 is equal to the weight. And now we solve for our torque equation, where normal 2 is going to be equal to the weight divided by 2 tan 60. Let's substitute in equation 0. Substituting in equation 0, we know that N2 is equal to the friction force. So we got the friction force substituted in here. And that is equal to W divided by 2 tan of 60. One other equation we did not write down is our fun equation. Our friction force is equal to, or in this case it has to be greater than or equal to, since we want the minimum coefficient of static friction, mu Sn. But this is just not any n. This n is N1. If we take a look at our picture, here is our friction force. We're talking N1 here. So we'll call that N1. N1, we know from equation 1, is just the weight. So let's substitute in equation 1 here. And now we have the friction force must be greater than or equal to mu s times the weight. Now we can equate these two equations. They both are friction equations. So let's go ahead and solve. We have our weight equation divided by 2 tan of 60 must be greater than or equal to our mu s times the weight. Well, we can eliminate weight on both sides of the equation. And now we know that mu s must be greater than or equal to 1/2 divided by the tan of 60 degrees. Which is 0.29. The static coefficient of friction must be greater than or equal to 0.29. And that ends our ladder example. Make sure you know how to do ladder problems.